Welcome everybody to Algebra 2, Section 4.4, Imaginary Numbers, Solving Quadratics with Imaginary Solutions. So let's start with the name Imaginary Numbers. It's actually a bad name because it gives the idea that these numbers are made up and less real than real numbers, or just not real at all. When the fact of the matter is that these numbers are actually very real. We just don't see them as often in our daily lives, but they still are real. They still work the same way, or work in a lot of the same ways that our quote-unquote real numbers work in. But let's dive in now and go ahead and work through it more, even though, once again, I just want to note that these numbers truly are actually real, even though they aren't part of the, quote, real number system. They are not fake numbers or anything like that, but they are technically called imaginary numbers. So equations such as x squared plus 1 equals 0 have what we call no real solution. And so if you remember, when we graph, we say that where it intersected the x-axis was our solution. Well, x squared plus 1 would look like this on a graph. And we note that it never crosses the x-axis, so we said there were no real solutions. Those solutions are not what we call real numbers. Instead, their solutions are what we call imaginary numbers. It still has solutions that can be helpful in many scenarios and can still be worked with. But in order to do this, we have to enter into a new system of numbers, a new set of numbers called the imaginary numbers. And so the imaginary unit, which we call I, to shorten up the name imaginary, because writing out imaginary is quite long. The I is defined as the square root of -1. So whenever we see I, we are referring to the square root of -1. And whenever we see the square root of -1, we will rewrite it as I to help us. Now this is really, once again, useful for working with square roots of negative numbers. What we call pure imaginary number is written in the form b times I, where b is what we call our real numbers, such as 3 or 2 or 8 or -8 or -5/2 or whatever. And I is the imaginary part. And what we're going to do is we're going to work on simplifying negative roots. And what we're going to do is we're going to rewrite the root of the negative number as root of -1 times the root of a. So very similar to how before we would say, like, the square root of 27 was the square root of 9 times the square root of 3. Similar here, we'll say that the square root of 27 is equal to the square root of, or square root of -27 is equal to the square root of -1 times the square root of 9 times the square root of 3. And it works incredibly similarly, except for now we just have the inclusion of the square root of -1. And so, for example, number 1, the square root of -9 is really the square root of -1 times the square root of 9. Now that's helpful because we can say that the square root of -1, we can rewrite that as I, we can rewrite the square root of 9 as 3, but we do actually switch the order around here, and we call it x equals 3I. Because once again, we want to do it in this form up here, where it's bi, the the real part is first, the numbers we're more used to working with come first here, with the imaginary part comes second. And so we end up getting this to still work. We just had to write it differently, whereas before we had said, well, there's no square root of -9. Nothing times itself is -9. And the true thing is that no number we've used so far times itself equals -9. But the number 3i times itself does, in fact, equal -9, oddly enough. So number 2, the square root of -196. We'll call this the square root of -1 times the square root of 196. Now, you definitely could write this part first, knowing that you're going to end up writing the non-I part first. And so the square root of 196 is 14, which I'm just going to go ahead and write it first in this part. And the square root of -1 is, once again, something we refer to as I. And you'll note that each time we do this, we'll always call the negative part the square root of -1. We're never going to look at that negative part and call it the square root of -4, the square root of -12. We're always going to call it the square root of -1 because that allows us to rename it I, which is very helpful for us to note our answer. So 3 is the square root of negative 5. So we're going to rewrite this as the square root of negative 1 times the square root of 5, which then we can rewrite as I times the square root of 5. And the square root of 5 can't be simplified, so we write this. Now note, I didn't write square root of 5 times I, whereas before, on numbers 1 and 2, I wrote the I last. The exception comes in when there's radicals. Radicals come after I. And we'll see this on our next problem as well, on number 4. So number 4, the square root of negative 80, we'll call this the square root of negative 1 times the square root of 16 times the square root of 5. The square root of negative 1 is I, the square root of 16 is 4, and the square root of 5 is the square root of 5. And so we write the part that became a non-square root real number first. We write the part that was imaginary second, and then we write the square root or the radical last. And that's the order we'll write these in. So on number 5, the square root of negative 32, we'll again call it the square root of negative 1 times the square root of 32, which becomes the square root of 16 and square root of 2. And so this becomes 4 times I times the square root of 2. The square root of 16 is the 4, the square root of negative 1 is I, and the square root of 2 is just square root of 2. On number 6, the square root of negative 192, we'll say it's the square root of negative 1 times the square root of 64 times the square root of 3. The square root of 64 is 8, the square root of negative 1 is I, and the square root of 3 is 3. Now we're going to use the square rooting method and get imaginary solutions. Once again, square roots of negative numbers. And we're going to write all numbers in the simplest form. So just like we learned in section 3, we're going to isolate our square term. This is done by subtracting 81 to get x squared by itself, and we get x squared equals negative 81. We still square root both sides to undo the square, and we get x equals positive and negative square root of negative 81, excuse me. And we note that the square root of negative 1, as we just talked about, or square root of negative 81, is the square root of negative 1 times the square root of 81. And this we can call positive negative 9, square root of 81 is 9, I, replacing the square root of negative 1 with I. And these are the two answers, positive and negative 9i. Number 8, our squared term is again x, so we will subtract 9 and then divide by 2. So subtracting 9 gives me 2x squared equals negative 8. Dividing by 2 is 2x squared equals negative 4. I said divide by 2, and then I wrote the 2, but it got rid of the square. Let me edit that real quick. Much better. And now I square root both sides to undo the square, and I get x equals positive or negative square root of negative 4, which we could go ahead and start calling the square root of negative 1 times the square root of 4, which is positive negative 2i. Let me write that a little bit more cleanly. Number 9 here. Once again, our square term is just x, so we subtract the 15 first. Whoopsie, it's wigged out on me after I hit undo. And then after that, we're going to go and divide by 4 and get x squared equals negative 6. Next, I will be square rooting both sides to undo the square, giving me x equals positive or negative square root of negative 1 times the square root of 6, which is just I times the square root of 6. I do want to note before I go on to number 10 that every time I write it is lowercase. That 100% has to be the way it's done, is lowercase. A capital I would mean something different. So we do use a lowercase I every time. And also, I do use the tail. You don't necessarily have to do that tail on the I. That's not required, like you making a lowercase is. But it does make it quite a bit easier to differentiate an I from like a 1, for example, when you have the tail on it. Next will be number 10, if it loads for me here. Number 10 is x squared plus 13 equals 1. We undo the 13 by subtracting it, and I get x squared equals negative 12. I then square root both sides to undo the square, and I get x equals positive or negative square root of negative 1 times the square root of 4 times the square root of 3. This is really just the square root of 12, but I rewrote it and continued splitting it up to make it so that way I could, in this next step, call the square root of 4 2 and the square root of negative 1i and the square root of 3 square root of 3 to call it positive or negative 2i times the square root of 3 as my two answers. Moving on to example 11. I will add 5 and then divide by 3. Adding the 5 gets me 3x squared equals negative 39. Oh, my apologies. For some reason I read that as negative 44, just completely omitted the 6 at the end, making this a triple digit number. Let's try that again. It would be negative 441. Then I'll divide by 3 on both sides and get x squared equals negative 147. Now if I square root both sides, I end up getting x equals positive and negative square root of negative 1 times the square root of 49 times the square root of 3. This results in x equaling positive and negative 7i times the square root of 3. Number 12. I would undo the 1 by adding it, and I get negative 2/3 x squared equals 18. And because a lot of us tend to struggle more with fractions than we do with non-fractions, I'm going to showcase this, that I would multiply by the reciprocal here to undo the multiplication of a fraction at negative 3/2, and where the negative on that fraction is matters not in the slightest, doesn't matter at all, because the fraction as a whole is negative. So 3 and 3 reduce, 2 and 2 reduce, and a negative times a negative is a positive x squared. On the other side, I'm going to put this 18 over 1 and reduce the 18 and 2 by 2 to become 9 and 1, and multiply the 9 times negative 3 to get negative 27. Now if I square root both sides to undo the square, I get x equal the positive and negative square root of negative 1 square root of 9 times the square root of 3. This is x equals positive and negative 3i times the square root of 3. Now let's talk about some powers of I. What would happen if you square I itself? That's a new one. So I to the first we know is just square root of negative 1, which is I. It's weird to call that I again, but remember writing the 1 is the same thing as not writing the 1. It's an invisible exponent. Now I squared would be the square root of negative 1 times itself, or the square root of negative 1 squared. And if you were to square the square root of negative 1, you would end up getting, actually I'll do this in a different color here. You would end up, as you square root the negative 1 and square that, you would end up undoing the square root and just getting negative 1. So it becomes a number we're far more comfortable with, we're far more used to and familiar with, because we've been working with the number negative 1 for years, since elementary school. Next, if we were to take I cubed, well, remembering that x squared times x to the first is really x to the third. When you have the same bases, the x, not the number that is being raised to an exponent, you add the exponents. When the bases are being multiplied, you add those exponents. And so with knowing that and reminding ourselves of that, I cubed is really I squared times I. And we noted that I squared is really 1. And so this is 1 times I, which is just I, because 1 times anything is itself. My apologies, it's negative 1 times I, which is negative I, because negative 1 times anything is just the negative version of itself. And so far we have I to the first power is I to the second power is negative 1, I to the third power is negative I. Let's figure out what I to the fourth is. So I to the fourth would be like I squared times I squared, adding those exponents of 2 to get 4. Knowing that I squared is negative 1, we can call this negative 1 times negative 1. And we've known for many, many years now that negative 1 times negative 1 is positive 1. Back to a number that we're far more familiar with. If we journey over to I to the fifth, we could call this I to the fourth times I. And actually, let me change colors here again. We could call this, as I mentioned, I to the fourth times I. And I'm choosing I to the fourth very specifically. Technically, we could also call it I to the third times I squared. but I'm going to call I to the fourth times I very specifically here. And the reason why is I to the fourth is 1. And so we have 1 times I, and we've known for many a time that 1 times anything is the other thing. So we end up with I again. And if I journey into I to the 6, I could rewrite this as I to the fourth times I squared. Once again, I could write it as other things. I could write it as I cubed times I cubed, I to the fifth times I to the first, but I'm choosing this on purpose, and you'll see why in a moment. And I to the fourth is 1, I to the second is -1. So 1 times -1 is -1. It might look familiar to something we just did a moment ago. I to the seventh we can rewrite as I to the fourth times I cubed. And I to the fourth is 1, I cubed is -I, and 1 times -I is -I. And I to the eighth could be written as I to the fourth times I to the fourth, which we know is 1 times 1, and 1 times 1 is 1. So you may have noticed by now that we just got the same exact 4 answers in the same exact order. We went I, -1, -I, 1. And then as we increased in powers, we just repeated it and went I, -1, -I, 1. And if you went I to the 9th, I to the 10th, I to the 11th, and I to the 12th, you get the exact same 4 things, exact same 4 numbers in the exact same order. I, -1, -I, 1. And this pattern, this cycle, just repeats continuously. So I could have I to the 64th, and I could know what that would be by tracking the pattern, knowing that it's always going to go in the pattern of I, -1, -I, 1 as we increase powers of I. This becomes helpful here as we try to look at a problem like number 13, I to the power of 15. And we say, okay, well, what would that be? Well, sure, we could just keep writing it out and go I to the 9th is I to the 10th is -1, and get to 15 eventually. But what about when we get to numbers like 76? Do we really want to be writing these out every single time we do them? Gosh, I don't, and I hope you don't either. So instead, let's think of a way we can do this. If we know they repeat every 4 powers of I, what we can do is break apart into powers of I to the 4th. I don't know why it says I squared there. I think that is a terrible idea to do I squared there. But instead we're going to do I to the 4th. And in order to get these into powers of I to the 4th, what we can essentially do is take the exponent that's there and divide it by 4. 15 divided by 4. Well, 15 divided by 4 is not a nice clean number. Instead, it ends up being a mixed number or a decimal. But we're going to write it how we used to write it in elementary school when we divided. We would say this was 3 with a remainder, which we wrote as R, of 3. We said it was 3 remainder 3. And for this purposes, I'm only concerned about the remainder, because that remainder tells me that this is really I to the 12th times I to the 3rd, because 3 times 4 is 12. I to the 12th would be very similar to I to the 4th and I to the 8th. At the next 4 powers of I later, you'll go back to being 1. And so this is really 1 times I to the 3rd. And we know that I to the 3rd is just -I. And 1 times I to the 3rd is just I to the 3rd. And once again, 1 times I to the 3rd would be -I, and that's our answer. And so what we can do on these problems to kind of shortcut through this part is we can divide the exponent by 4 because the cycle repeats every 4 powers of I, and our remainder tells us which power of I we're left with. So let's try this on number 14, I to the power of 62. We'll take 62, we'll divide it by 4, keeping track of the remainder, and we end up getting 15 remainder 2. And realistically, I don't even care about this 15. I only care about the remainder on all of these problems. The other number is irrelevant because it's going to end up being I to the power of 15 or I to the power of 60, which is just 1 anyway. And so as we look at this remainder of 2, which once again, we don't care about that 15, we only care about the remainder, this tells us it's going to be I squared. And I squared is equal to -1. Meaning I to the power of 62 is equal to -1. Same thing would happen here on I to the power of 76. We take 76, we divide it by 4, and we say that this ends up being 19 with a remainder of 0. Well, crap, what do I do now? This method doesn't work now because we said the remainder was our exponent of I. So what do I do when it's a 0 because we don't have an I to the power of 0? 0 just tells us that we are using I to the 4th. And I to the 4th let me try this here again. I to the 4th is 1. And the reason why 0 tells us just I to the 4th is being used is because if we're doing remainders here as we divide by 4, the only possible answers to that could be a remainder are 0, 1, 2, and 3. You can't have a remainder of 4 if you're dividing by 4. If 4 remained, you would just divide by 4 again, because this is secretly 18 with the remainder of 4, which would be kind of very weird to say, called 18 and 4/4, which is not inaccurate to, because it equals the same thing as 19, but it's quite an odd way to word it and write it. So instead we just say 19 remainder 0, and note that the remainder of 0 just tells us it's an exponent of 4 on I. I to the power of 43, we would take 43 divided by 4, and we get 11 with the remainder of 3. Once again, I could not care less what the number before the remainder is, because the remainder tells me all I need to know, that it's I cubed, and knowing that it's I cubed means that it's negative I. So if you can remember this pattern for each of these powers of I, and remember that you just need to divide by 4 for the exponent, and then take your remainder, you can simplify any problem. So if I were to give you I to the power of 12,982, some random number I just came up with off the top of my head, you could figure out what it would be by dividing by 4, taking the remainder, and going from there. Now, a lot of us are going to use a calculator for this, and so it's important to know what those remainders equal to as decimals. So for example, the remainder of 3 would be the same thing as 0.75. The remainder of 2 would be the same thing as 0.5. The remainder of 1 would be the same thing as 0.25. And maybe the most straightforward would be the remainder of 0 would be 0.0, or no decimal at all is shown because the decimal is only 0. Moving on here to number 17, let's simplify these expressions while we multiply these together. So 4i times 7i, we multiply the 4 and 7 together and the I and I together, very similar to what we did when there was x's involved. So 4 times 7 is 28. I times I is I to the power of 2. We add those exponents. And I know that I squared is negative 1. So this is really 28 times negative 1, which is negative 28. Number 18, as I multiply 2 of these together at a time, negative 4i times 2i is negative 8i squared. And now I can multiply that with negative 9i. And I end up getting 72i to the third. Noting that I to the third is really just the negative version of I end up having this equal negative 72i. Writing the negative at the front just like we normally do. Number 19, we first have to cube 2i. Now that is not just 2i cubed. Instead, that it says 2i times 2i times 2i. And 2i times 2i times 2i is 8i cubed, because 2 times 2 times 2 is 8. And 8i cubed would be multiplied with 5i, which would result in 40i to the fourth. Remembering that I to the fourth is just 1, this is 40 times 1, or 40. On number 20, once again, we have to square this, which means we square both the I and the square root of 3. We do that when there's multiplication or division inside the parentheses. We can't just do this and take the exponent to each exponent inside there. And by take it to, I mean multiply with each exponent existing currently. So I to the first becomes I squared as we do 2 times 1, for example. And when we have I squared times square root of 3 being squared, this is really I squared times 3, or 3i squared. Our other one right next door, right here, would be negative 8 times negative 8 is positive 64, and I times I is I squared. And so I'm just going to rewrite that right here. Oh, I should do the orange to match what I did a moment ago. Keep consistent. Now I know I squared is just -1, so this is -3, because 3 times -1 is -3. And this is -64 for the same reason, because 64 times -1 is -64. And as I multiply these two together, I end up getting the positive number 192. Number 21, the square root of -18 times the square root of -10. And we may think right away, I do myself oftentimes, of saying this is going to be the square root of 180 because -18 times -10 is 180. Perfect. I got rid of the negative imaginary numbers. We're back in our normal numbers that we're used to, the quote-unquote real numbers. Oh, awesome. Good for me. This is actually wrong. So don't do this. I'm going to showcase the answer you would get from this and compare it to the actual answer that you would get. So the answer you would get from this is you'd call this the square root of 36 times the square root of 5, which would result in it being 6 square root of 5. Now table this for just one moment as we do it the correct way over here. So we would need to call this the square root of -1 times the square root of 18. And we need to call the other one the square root of -1 times the square root of 10. In doing this, we can note that it is I times the square root of 18 times I times the square root of 10. And as we multiply these together, we do I times I to get I squared. And we do square root of 18 times square root of 10 to get square root of 180. Now, this, from here, we would say I squared is -1. Square root of 180 is square root of 36 times the square root of 5. And we end up getting, as a result here, -6, square root of 36 is 6, times -1 is -6, times the square root of 5. And this is our true answer. Note, the other one we got is lacking a negative. So because these are two different numbers, clearly one of them must be wrong, and it is this one on the left. Now let me explain the reason why that one is wrong. Why must it be, quote unquote, more complicated than we would think initially? Well, the reason is that the product property, aka multiplication, what says we can multiply the product property for square roots or roots in general, does not include negative numbers. The product property only holds, or is only true, only works when the numbers are positive. And so we first have to go through this orange and purple steps here on the right to make these square roots positive numbers, to express these square roots as positive numbers. And so what we do is we separate out the I, the square root of negatives, away from the positive numbers to make these positive numbers. And now that they're positive numbers in the square root, now we can multiply them. So long story short, you can't multiply square roots of negative numbers together. You can only multiply square roots of positive numbers together. And so we have to make it so that way they're square roots of positive numbers like we did over here in order to multiply. Once again, this is wrong. The one on the right is accurate. So that's what this is saying is watch out. Rewrite negative square roots, or square roots of negative numbers might be a better way to phrase that, as imaginary numbers before performing operations, such as multiplication. Number 22, we see the same thing here. So knowing the pitfall that happened last time, we're going to go ahead and say that this is the square root of -1 times the square root of 24. That this is the square root of -1 times the square root of 3. And this is the square root of -1 times the square root of 2. And that this ends up being I times the square root of 24 times I times the square root of 3 times I forgot the I here, times the square root of 2. And now as I multiply each of these together, the first two together, let's say, because we multiply two at a time, I get I squared times the square root of 72. And if I multiply that by I times the square root of 2, I end up getting I cubed times the square root of 144. Noting that I cubed is really just -I, and the square root of 144 is 12. And I can reorder that, which I will, to be -12 times I, or negative 12i. Remember, a negative times a positive is a negative, and we usually put that negative out in front. So this ends up being negative 12i. So in closing, I just want to restate that imaginary numbers are not imaginary at all, actually. They are very, very real, even though we don't call them part of the real numbers for our set of numbers. So they're not part of the real numbers, but they're not fake or made up either. So we classify them as imaginary, but they are numbers that we do see. We just don't see them often in normal everyday life. They are usually reserved for much more complex work, but not fake or non-real work. And that wraps up Algebra 2, Section 4.4.